I think today is a very good day in the University of Oviedo. We are very happy with your visit, and this is a great moment in one of the greatest faculty of the University of Oviedo. Thank you very much. Thank you for your generosity. We are very thanks for you. Thank you. Es un gran momento para esta facultad y para esta universidad, o sea que disfrutémosle. Muchas gracias.
Thank you, Rector, for your welcome message. Authorities, Dr. LeCun, Dr. Hassabis, welcome here to our school. It is an honor to receive such important personalities in our School of Computer Engineering, and especially this academic year, 22-23, in which we celebrate our 40th anniversary. We have always believed, and have let our students know, that the university is more than just a place to study. It's also a meeting place where people from different fields may come to discuss interesting things. Today, we have the amazing opportunity to talk with you regarding your contributions to artificial intelligence, which have made you earn the Princesa de Asturias Award for Technical and Scientific Research. Your curriculums are well known by our audience here and by our audience upstairs. But let me briefly introduce you to them. Yann LeCun, Geoffrey Hinton, and Joshua Benjur are considered the godfathers of artificial intelligence field called deep learning. Deep learning is based on the use of neural networks for, among others, voice recognition, computer vision, and natural language processing. It has achieved significant advances in fields as diverse as object perception and machine translation. They were all distinguished in 2018 with the Turing Award granted by the Association for Computing Machinery. Demis Hassabis is CEO and co-founder of DeepMind, one of the largest artificial intelligence research companies in the world. At DeepMind, Hassabis has created a neural network model that combines the capabilities of those networks with the algorithmic power of a programmable computer. In 2021, the DeepMind team managed to predict the structure of more than 350,000 human proteins with a very high degree of accuracy. The achievement was featured by Science magazine as Scientific Discovery of the Year. And now let me give you some context information about the audience itself. The audience is a rich combination of professors, students, and researchers from various departments and degrees, such as computer science, obviously, but mathematics, physics, statistics, and industrial engineering people is also present here. There are also professors and researchers who have artificial intelligence as their main field of work. And finally, an important number of students, mainly from the software engineering and web engineering studies we teach in this school. We might start the question and answer section of this event right now, but if you rather want to address the audience, to give any message, any kind of message, before they start, I hope, asking questions, I'd be honored to give you the floor.
Actually, I think there is plenty of videos you can watch with our work, and so since we are in the same room, I welcome your questions, and I look forward to answering them.
Yes, so likewise, I think why don't we go straight into questions?
Okay,
yes.
Perfect. So, first question. I'm going to pose the first question, and I'm going to try to think as if I were a student sat there, one of our students of our software engineering degree. So my first question is thinking as a student as a possible future. So how important as software engineers in your teams could be one of my first questions. What are the most important skills you think they must have, besides the typical ones that are expected for software engineering? And other positions, other vacancies in your teams right now?
Okay, I'll start by the last question. So this year is not a very good year to get a job in the tech industry because of the macroeconomic situation. So we're still growing, both of our companies, but not nearly as fast as in previous years. But hopefully next year will be better. So by the time you graduate, things will get better. So in terms of what skills are required, there are of course people in our groups. So we both work on research and long-term research, and that takes a very broad collection of different skills. Some of it is pure software engineering. A lot of it actually very, very sort of low-level hardware banging kind of things, programming GPUs and things like that. Some of it more on the compiler level, etc. And then you work all the way up in the stack if you want. And then there are people who are, writing tools for deep learning research and development, things like PyTorch in our case, JAX, I think DeepMind is used mostly. And then of course people developing new learning paradigms and architectures and algorithms, and people devising kind of new ways of approaching the problem of AI. And for a lot of those things, the type of skills that are required are not necessarily traditional computer science skills. In computer science, in many countries, not so much in Europe, fortunately, but in the US particularly, traditional computer science curricula do not have enough continuous mathematics, essentially. Because the underlying mathematics that is necessary for machine learning and AI is something you would traditionally learn in electrical engineering or control theory or something like that, or in physics, statistical physics, but not so much in computer science. And so if you are, I assume many of you are graduate students already, but if you are an undergraduate listening to us, you should probably take as many courses in physics and signal processing and electrical engineering, and perhaps mathematics, things like linear algebra and things of optimization, things of that type, that you can, because those are the fundamental tools that are necessary for machine learning AI as it evolves. And to some extent, traditional computer science, of course, is very useful, but it's only part of it. Thank you.
Yeah, maybe I can just add to that. I think one of the reasons AI is such a fascinating field is because it combines engineering and research and science. So I like to call it an engineering science because first of all, you have to build the artifact of interest, and then you can study it scientifically. So I think it involves both kinds of thinking. And then the only other recommendation I'd add to Yann's is that if you are doing a master's or PhD in machine learning, I would also encourage you to learn another subject as well, whether that's biology or economics or physics, so that you can apply the machine learning. I think there's going to be a lot of advances applying the machine learning skills to another field and interdisciplinary between two fields. I think that's where there's a lot of low-hanging fruit, and I think there's a lot of easy progress or good progress to be made in those areas. And that's something we do at DeepMind. We have a whole team now, which we call the AI for Science team, and that's where things like AlphaFold are done, but we also work on many other subjects like quantum chemistry, fusion, mathematics, applying AI to those subjects, and it's a really fun thing to do, and I think it's going to be a huge growth area in the next decade.
You forgot your favorite field, neuroscience.
And neuroscience, yes. Well, that one's so integral. I regard it as part of the core. But you're right, of course, applying AI to neuroscience as well as taking neuroscience ideas from AI. But I consider that to be a fundamental part of AI anyway.
Right. So, just to reinforce what Demis just said, the potential of applications of deep learning and AI to science is mind-boggling. This is an area that if I was a young student today, I would have a difficulty choosing between making conceptual progress in AI or sort of applying AI to various scientific fields. In fact, you're doing both. We're doing both. So
yeah, it's a lot of fun.
It's a fascinating area. You shouldn't get the idea that everything has been discovered in AI. I think we are on the cusp of sort of a new revolution, if you want, that you can be part of.
Thank you. Okay, now it's your turn. Questions?
Thank you. First of all, I would like to congratulate you on this award. I think it's clearly very well deserved, and I think your work is really inspiring for all of us. And I have two questions. The first one is regarding the architectures of neural networks. It seems that in the last few years, for instance, transformers or generative adversarial networks have led to some advances in fields that were difficult for neural networks so far. So I would like to know whether you think that we should start looking for different architectures. Is this essential for advances in machine learning? And the second one is regarding quantum machine learning. Is this something that you are, because my work and my part of my teaching is in quantum machine learning, quantum computing in general, is this something that you are exploring in your companies? Is this something that you think that in the future will be important in the field, or is just a fashion, or I don't know? Thank you.
Okay. You want to take the first bit? Second?
Sure. So I'll answer the second question first.
Yeah.
I'm somewhat skeptical about quantum computing, but I think I find it sufficiently interesting to actually kind of work on it as a sort of more exploratory things. I think the practicality of it is still quite far in the future, at least when I talk to my colleagues who are more specialists of that. I actually have a recent paper with Seth Lloyd from MIT, who is a quantum computing person, where we sort of make some parallels between what we call unitary neural nets and quantum computing. But in terms of practicality, I don't think there will be consequences in the short term or even the medium term. But that doesn't mean it's not interesting to work on it, obviously. But I can't say that we have a big effort on it. It's more like, let's see how interesting this could be. To your first question, I think there is still a lot of innovation to be done in architectures of neural nets. I see. So you mentioned transformers. So there are things, properties of certain modules in neural nets that are interesting. Convolutional nets are equivariant to shift, right? Transformers are equivariant to permutation. So that's a very powerful tool, because now you can have a neural net whose output will not depend on the precise order in which the inputs are presented. And that's very interesting when you have sort of object-based representation that does not come in a natural order. The other advantage of transformers also is that they sort of subsume graph neural nets, which I see as a major conceptual advance in the last several years, where the graph of connection between the various modules in a neural net are dynamically determined by the data, essentially. And certainly a transformer kind of takes this to the extreme a little bit. What that gives you also is a way to control the function of a neural net. So if you take a subset of inputs of a transformer, and you view this as inputs, and you can view the rest as configuring the input-output relationship between the first set of inputs and the outputs. And so that gives you sort of a configurable module, which is extremely powerful and flexible. So a major advance. So for vision, for example, my favorite kind of architecture is a few layers of convolution followed by transformers, which there was a very good paper by a student at FAIR in Paris called Nicolas Carillon, who is now a scientist at FAIR called DETER. This was architecture for object detection that was based on this idea, and there was a lot of work in that direction. But I think we're still missing new ideas in terms of architectures, and certainly in terms of learning paradigms like self-supervised learning, which I've been advocating for a number of years.
Yeah, so maybe I can just add to that. I think starting with quantum machine learning, I talk a lot to our colleagues at Google who work on this, who some of the most advanced work, and there's a lot of effort trying to combine the two fields. We're actually, I think, is another interesting area to apply machine learning to. So we're, for example, looking at quantum error correction. I think that's a good, potentially machine learning can help there. But as to whether quantum computers will be useful for machine learning, I'm sort of have the same view as Yann, which is I think that AI is advancing faster, so probably that will be first. So I always have this joke with my quantum friends of like, well, if we had a quantum computer, of course that would be helpful for building a quantum AI system, for sure. On the other hand, if you had an artificial general intelligence, then you could tell it to build a quantum computer. So, if I was to bet, I would bet it's going to be that way around. So we definitely want quantum computers, but I think AI will come first and maybe will help in the design and the creation of those systems. So, but we have to keep what we do. We have some quantum. We have a very small quantum computing group in DeepMind, and we just keep an eye on that whole field. And if it starts looking like it's accelerating faster, we will put a big team on that. And then, of course, we're very interested in quantum domains like quantum chemistry as another application area. So we do quite a lot of work on quantum systems, quantum mechanical systems. And then, yes, on the architectures, of course, transformers, which sort of developed out of, as Yann was saying, graph neural nets and attention networks. They've been very, very powerful, probably more powerful than we imagined to begin with. And it makes a lot of sense why they're so powerful. But I think there's still quite a lot of innovation to go. We haven't really dealt with large external memories, or how are you going to do sort of retrieval along with the transformer networks. So these are the kinds of things that we're researching, and I think there's still quite a lot of answers there, as well as pushing the current architectures further.
Yeah, in fact, a few months ago I posted a sort of a position paper that tries to foresee what type of macro architecture might be useful to integrate various modules such as transformers and others in an architecture that would allow machines to reason and plan and things like this, which most current deep learning systems really are not appropriate for, including large language models. I realized I forgot to answer. You mentioned GANs. Okay, I used to be a big fan of GANs, and I'm not anymore. GANs, I think, are conceptually a very interesting idea, and it's certainly delivered in terms of image generation, although now it's being basically overpowered by diffusion models. But in terms of using GANs as a way to learn representations, to learn features, to do self-supervised learning or unsupervised learning, they've basically been a failure. the results have been extremely disappointing. So it's conceptually very interesting, but I don't see this as sort of a key advance anymore.
Thank you. More questions?
Hi, I'm a software engineering student, and well, I'm very early in my degree, so I haven't taken any course related to artificial intelligence yet. So I have a question. I've read some news articles about the fact that you're trying to use artificial intelligence as a means of battling fake news and like disinformation in media and everything. So I would like to know how that can be used to achieve that purpose.
Right, well, it's a very difficult problem because, first of all, there is no clear definition of what misinformation is. So if there was a system that was able to establish whether a text is factually correct, you would not want to use it, because on social networks people exchange all kinds of information that is not factually correct and is perfectly fine. People exchange stories, myth, poetry, jokes, all kinds of things that don't correspond to reality, but are just fine for people to exchange. And so the question is, what is dangerous misinformation? And this is not a question for AI researchers like us. It's a question for people who study human communication, sociology, etc., of which there are many at companies like Facebook and Instagram and YouTube and others. And so it's a very difficult question, but it's more a non-technical question than a technical question. Once the non-technical question have been determined, then there is the question of enforcing those policies, the content policies. And the sad news is that although current technology is quite good at detecting things like that is illegal, particularly in Europe, like pedophilia, hate speech, things like that. Although it's not perfect, it's very far from perfect, particularly when it's applied to all the world languages. It's relatively easy to do in languages like Spanish and English that are very widely spoken in the world. But there is a lot of languages that people use on social media that are rare, and it's very difficult to have enough training data for things like hate speech detection there. So those systems are not perfect. But they kind of work. So for example, the proportion of hate speech that is automatically taken down by AI systems before anyone sees it on Facebook went from about 40% 4 years ago to above 95% today. And it's entirely due to progress in transformers, essentially. So self-supervised, pre-trained natural language understanding systems, they've become so good that now we can really use them for content moderation. Again, it's very far from perfect. Misinformation is a much, much harder topic because one person's misinformation is another person's truth when it comes to things like politics and religion and things like that, right? So we don't know what the correct answer is.
More questions? No more questions, really? Okay.
You talked before about the skills of a computer software engineering, and you give some recommendations for the software engineering students. But I would like to ask you for an advice for those students that are starting their research career. Maybe I don't know, for example, someone that is on their PhD studies or something like that, like me, that I am starting, I don't have a lot of publication, I have to read a lot of articles, learn a lot of things. What advice would you give to those people?
Yeah, I would echo what I said at the first question, which is that if I was a new starting PhD student now, of course you can try and advance the state of the art in AI itself. I think that's quite hard today because of the amount of compute needed and engineering, and we have very large teams at these kinds of companies, and it's pretty difficult, I would say, to be ahead on that, although you could come up with something like GANs, which an individual PhD student did do, a very smart one. But I think that's getting harder. What I think is getting easier is to apply the cutting-edge state-of-the-art machine learning that's freely available now, open source, and figure out what to use it for, and then become pretty expert in another subject, so that you can ask the right questions of where can it be applied in the most meaningful way, which is an art in itself. It's not simple. It's not as simple as saying, chemistry will just apply machine learning. You have to pick the right question, and often the chemistry or the other subject the experts won't know either, because they don't know enough about machine learning. So in my view, that's the best place for the next 4 or 5 years, I would say, is to, if you're starting a PhD or something like that, is to pick another discipline you really are interested in and get very deep in that, as well as your machine learning and software engineering skills. And then I think you'll be able to do some amazing things.
So I actually have a slightly different opinion from Demis on this. We agree on almost everything, but sometimes it's kind of slightly different flavors. So I actually think that you can make meaningful contributions to advances in AI, because some parts of it, of course, relies on just a lot of computation, very large models and things like this, and you would have a very hard time making progress there unless you are at a lab like FAIR or DeepMind, where you have a lot of computing resources. So the type of progress you can make, or the contributions you can make, are conceptual contributions. You don't have to beat any record on language translation or anything like that, or computer vision, but you can come up with new conceptual ideas that you can demonstrate the value of on toy problems or smaller problems, particularly when it comes to things like agent systems, so systems that don't just perceive, don't just generate, but can generate actions, for example, and things like that. We're missing a lot of conceptual building blocks for that, and so this is an area that's where you could probably make a lot of contributions without having access to enormous computing resources. A lot of good ideas come from academia. So things like you mentioned GAN that came out of Mila in Montreal. Another idea that came out of that lab is the whole idea of attention. I mean, it existed before, but it was sort of demonstrated as really being powerful by Mila. So a good example of Mila is that there's a famous paper by Badanao, Cho, and Benjo, Joshua Benjo, a co-recipient of the award with us, demonstrating that you could use attention circuits in a system to improve the performance of translation systems for language translation. The previous approach in neural nets for translation was a gigantic multi-layer LSTM that was built by Ilya Sutskever at Google that required enormous resources and a lot of engineering to make it work. Very impressive work, but a little bit impractical for that reason. And what the Mila paper showed is that you don't need that system to be enormous. You can basically shrink it down to a relatively small size and still have it perform better. Then a team from Stanford, an academic team, won the WNT competition, the translation competition, just a few months later, using the technique that was proposed by Mila. And when that happened, the entire industry jumped on it. So every single company, Google, Facebook at the time, who wasn't called Meta yet, Microsoft and everybody else started using those attention systems to build translation systems. And they became kind of the standard method. So that's a good example of ideas from academia really having a big impact. As soon as the first results came out of Mila, Joshua Benjo told everybody in his lab, stop working on translation, because you're never going to be able to compete with, Google and Facebook and Microsoft. So we met our mark, showed the ideas, now it picked up, and we're out of it now. So you have to pick your topics so that you can make meaningful contributions, and that means kind of upstream conceptual contributions as opposed to beating some record on some benchmark.
Yeah, we're actually in agreement, because I agree with that, by the way. So yeah, I was just saying I think the easier approach is the multidisciplinary one. Of course, this is all true. I fully agree with what Yann says, that of course there's many contributions from academia, and I would go more conceptual, more theoretical than practical, just because that's what big companies can do more easily. I'd also say another actually key area if you want to be in a pure AI advances is actually analysis and interpretability and safety of these systems. I think we need a lot more students being interested in those topics, because I think that's going to become an increasingly important question as we deploy these systems into the real world, how we can do that in ways that are controllable and understandable for the general public and for regulators and governments and other things. And I think we're still very basic on that kind of front of actually understanding what these systems can actually do. So that would be another area I would be looking at if I was a student today. So there's lots of work to do. Plus, the other thing you could do is also apply for internships at many of these places, and that will also, and DeepMind, we're still hiring, by the way, to answer that earlier question. So there are other ways to also gain access to that kind of industrial approach if you want to.
There are internships and also residency programs. Yeah. So if you're not sure whether you want to do a PhD but you want to get involved in AI, you can apply to one of those residency programs, and you're basically engineer in one of the AI research groups. You can get some publications, and that will allow you to apply to top PhD programs later.
Thank you. More questions?
Hi. This question is for Yann LeCun about a thing that you're reading in your book, La belle histoire de l'intelligence, where you explain how human remembers things, and you talk about different memory circuits. And in a tweet you published 1 month ago, you say that one of the most breakthroughs in the last 10 years was the differentiable memory. So I've been reading some articles, but I think, don't you think better that we are reproducing human problem for remember? Because I think we have many data systems, we have good information, and the memory is only keeping the most. I don't know if what my question is.
Yes, I understand your question.
Yeah.
Well, so Demis alluded to this earlier, that so in the brain of at least of mammals, there is a separate subsystem for kind of remembering things for more than about 20 seconds, called the hippocampus, right? So it's in the middle of the cortex, is connected to just about everywhere in the cortex. And if you don't have a hippocampus, you basically cannot remember things for more than about 30 seconds. And so it shows fairly clearly that learning a skill and remembering things are kind of two different functions that you might need two different architectures for. And I was really very interested by work that was simultaneous actually at FAIR and DeepMind on essentially augmented a classical neural net with an associative memory. So at FAIR this was called memory network, and there were like multiple versions of it. At DeepMind I think it was the differentiable neural computer, which was a very similar concept. And those two things were developed in parallel. Actually they appeared on arXiv within 3 days of each other. And I think that concept is very powerful. I think it was somewhat underdeveloped in the following years, in the sense that people started working on kind of things that were different. But to some extent, you can see the heritage of this in the work about transformers. So transformers, the essential component of a transformer is an associative memory. And the reason why transformers can be scaled up and can learn lots of different things that seem to be kind of factual and unrelated to each other is because the underlying module is basically an associative memory. And so the question I have that I'd like to solve is, do you need a completely separate architecture to kind of remember things than a traditional neural net, including transformers, or not? I think the answer is probably yes. And the reason is, for machines to be intelligent, they will have to be able to make predictions about the consequences of their actions and the evolution of the world. And when you observe an event in the world, so the event, for example, would be, I push this glass, your representation of the state of the world is largely unchanged except for the position of this glass. Right? And so it would make sense to have some large memory that stores your idea about the state of the world, and this memory gets modified just slightly as a consequence of an event you perceive or that you're being told about. So that's where I think you need a separate memory module. Now, the thing is, a memory module like this would be an associative memory, which is somewhat unreliable, like human memory, right? We don't have such a great memory for facts, unless they are facts that are really important for our life or our survival. And so you would probably also need to augment those AI systems with a memory that is similar to us as pen and paper, something which is similar to a database, a classical, computer database, where you can actually store facts. And in fact, there is quite a few attempts at this kind of thing, where you have dialogue systems, which instead of having stored the entire knowledge of the world in the weights of some transformer, they actually go and ask a database or retrieve information in Wikipedia or something like that to try to produce answers that are factually correct. But this is still work in progress. I mean, most dialogue systems today really don't do this very well.
So maybe I can add to that too. I mean, I spent my whole PhD working on the hippocampus. Right. So this is my area. I mean, this is prior to even DeepMind. So I did my PhD in neuroscience, actually. So I studied the memory system, and that was one of the reasons I studied that system, because I knew that AI systems did not have this kind of associative memory, and I felt that they needed to. So we've been working on this for 12 years or more, and I think that's still missing, although some aspects of that are in transformer networks. But I still, and we actually have our own large models that have interesting extra capabilities, one called Retro, where you actually go and retrieve things as well from the internet or do a Google search as well as whatever is in your neural network. And I think we have to augment those even further with associative memory systems. My belief is you would need an extra module or different way of computing. And so from the very beginning, we've had this idea that you need two sorts of systems. One is like these neural networks. They're a bit like your associative cortex that learns from many, many examples, but also you need something that's more like an episodic memory system, like your hippocampus. The other reason that's important is because they can learn with very few examples, one-shot learning, yep. It's sometimes called. And in the human brain, that's the hippocampus. You can remember from one event, like I'll remember today's lecture, later on, I don't have to repeat this 1,000 times, right? And there are really interesting other things, concepts in neuroscience that have not yet been, I think, we've tried to experiment in them in AI, but we haven't fully worked out how to implement them. For example, memory replay. So, when you go to sleep, one of the theories of learning is that your brain, your hippocampus, replays many of the memories, the important memories that you've had during the day or in the last few days, and then that gives your cortex more chances to learn from those experiences. So you're kind of reweighting the experience, right? You're upweighting that effectively, and of course you can see for survival that would be very important, right? If something dangerous happened, then you need to learn from that thing without having to experience it many, many times, because it would be too dangerous. So you could see why that sort of system would have evolved and why it would have been useful. And I think there's other things too, where we have this system called GopherSight, where it's a large model, and more recently one called Sparrow, where the language model cites the references of where it got that information from, right? So that's a little bit more like an episodic memory too. And actually something that Yann sort of written recently, but I've been thinking about for a long time, is these things like world models, where you have a model of the world around you. And it turns out for my PhD work that the hippocampus is not just important for memory, it's also important for imagination, so forward planning. So it's not just recalling the past, it's imagining the future. So both things need the hippocampus. That's what I showed in my PhD, was that with these patients without hippocampus, they can't imagine the future either. If you tell them what are they going to do next week, they can't come up with a plan like a healthy person would. So it's very interesting, these ideas that I think are still very relevant for machine learning and are not yet solved.
Thank you. Do we have time for a final question? Yeah? One final question.
Yeah, hi. So I'd like to address this question to Dr. Hassabis, because apart from a software engineering student, I'm also a bit of a chess enthusiast.
Oh, cool.
So I'm aware of your background as a chess master and the development of AlphaZero by DeepMind. And it's been said that it has achieved a kind of human or creative style of play, even said by Magnus Carlsen himself. So I'd like to ask you, how does an artificial intelligence that hasn't been input with any games from previous human players and has been self-taught achieve this kind of knowledge?
Yeah, thanks. Thanks for the question. That's a great question. I love talking about chess and AlphaZero, of course, so I could talk about this for a long time. And I've talked to Magnus Carlsen about this, and he was one of the first people. We actually gave access to AlphaZero to the British chess champion, and who I knew from when we were both young, and he had a sort of background access to it and wrote a really good book called Game Changer, which explained all the new strategies that AlphaZero came up with. And Magnus Carlsen was the first person to read the book, and then he implemented it in his own play. So it's been amazing to see. But to answer your question, I think the reason it came up with that style is, and I would summarize the style for those of you who know how to play chess. Chess computers, the old-fashioned traditional chess computers, played a very ugly style of chess in a way, because they were very materialistic. So they would try and win a pawn. The joke was computer sees a pawn and it tries to grab a pawn, and then it will hold on and defend really well. And because it doesn't make any tactical mistakes, this can be quite effective. But to a human player, this looks very ugly aesthetically. Instead of that, AlphaZero favors mobility, not materiality. So it favors lots of options for its pieces. And I think maybe it's just lucky that style seems very elegant to us as humans, right? So it's not something that AlphaZero is programmed to do, to play in this open style. But it's something it discovered. And the nice thing is, and maybe that's the beauty of chess, is that turns out to be more effective in the end than this ugly style. So chess players, that was unexpected bonus to doing the whole AlphaZero, that in the end turns out chess is beautiful fundamentally. So, but it took AlphaZero to show that. So, but it didn't have to be that way, but it just turns out that it is that way. So it's very nice to see.
Yeah, I can't comment much about chess because I'm an absolutely terrible player. But I think what's interesting is to try to think about the sort of different types of tasks that turn out to be really complicated for computers as opposed to humans. And so we invented those games, chess and Go, because they are hard for us. We don't have enough episodic memory to do tree exploration, for example, as humans, and we're not fast enough at computing to do it. And so those games were designed to be hard for us. And it turns out we suck at it. We're terrible at it, right? I mean, AlphaGo demonstrated that.
Well, I wouldn't say we're terrible at it. That's where Lisa Doll is. I mean, they're extremely good. Magnus Carlsen is extremely good at chess. They're just not quite as good as the computers.
No, but the point is, they used to think that the best players at Go were something like 2 or 3 stones behind God, right? The best optimal player. In fact, no, we're like way behind humans. humanity is really way behind that, and that's one of the things that AlphaGo has shown. Something similar with chess as well. So I can certainly get totally wiped out by, a $30 gadget, a €30 gadget that plays chess. So then there is, other types of tasks that are considerably more complicated. So things where the game is not fully observable. So things like poker, for example. There's some work also at FAIR on diplomacy, which is a strategy game where you need to communicate with other, form alliances with other players. And then there is the real world. And in the real world, a lot of the techniques that work well for games don't really work very well, because the amount of interactions you have to have in the real world becomes so large that it becomes impractical. So there are, so I'm getting into dangerous territories being on the panel here with Demis, but the success of reinforcement learning in sort of real world application, unless you have an application where you can have enormous amounts of trial and error, has been very disappointing. We can't use RL to train cars to drive themselves, for example. It's just not good enough. Whereas, we can learn to drive a car in about 20 hours of practice. So obviously we're missing something big there that is not properly reflected in either supervised learning or reinforcement learning, or even the type of self-supervised learning that we can currently do with transformers, for example, that work really well in the context of natural language processing. The big question, I think, for the next few years, perhaps decade, in AI is how do we get systems to learn predictive world models that allows us to plan, not just in situations where the world is fully observable and deterministic, but the world is the real world, and there is a lot of uncertainty about it. And this is also a problem that a lot of people at DeepMind are interested in, of course. I think making progress in that direction is what will bring about the next revolution in AI.
Thank you. I'm afraid we have to finish, because you have a very strict agenda to follow. So let me tell you a few words about what's going to happen immediately after. We are going to greet the other part of the audience on the second floor. So please stay here for a few minutes so we leave. Okay? And then in 15-20 minutes we will join you outside to have a family photo with them. Okay? So please don't leave the school. And obviously before they leave the room, I request you a close applause. Okay, so we have to go upstairs.